This is Taylor Couette Flow by Colin Shale, Anthony Tefano, and Brittany Scaglione. Taylor Couette Flow is a special application of Couette flow where the fluid is being moved by the rotating cylinders rather than by a moving parallel plate as discussed in class. For our application, the inner cylinder was allowed to rotate while the outer cylinder remained motionless. Fluid experiencing Taylor Couette flow moves laminarly until the angular velocity increases past a certain point. At this point, a vortex-like effect is created in the fluid, causing turbulent flow. Taylor Couette uses a Taylor number instead of a Reynolds number. This Taylor number is a combination of the Reynolds number, the ratio of angular speeds of the cylinders, and the ratio of the radii of the cylinders. For our experiment, we used 4 bottles of Karo corn syrup, 2 circular plastic containers with different diameters, a ruler for the creating of circular motion, food coloring, syringes for injection of dyed corn syrup, and assorted hardware to connect plastic containers. There were 4 different trials using a combination of 2 different orientations at 2 different speeds, as listed here. After trial preparation, the inner cylinder was rotated clockwise for approximately 10 seconds in one direction, after which the cylinder was rotated counterclockwise for an equal amount of time. The final position of the die or streak indicates whether or not the flow at that radial distance was laminar or turbulent. For the sake of time, these videos were sped up, but in this video, pay close attention to the location of the dots in the beginning of the video and in the end of the video. In this video, notice that the dot closest to the inner cylinder has the highest velocity, and the dot furthest from the inner cylinder has the lowest velocity.
Various assumptions were made to simplify the calculations. We assumed that the principle of no slip holds at vessel walls, implying that the velocity of syrup at the inner cylinder matched that velocity of the inner cylinder. We also assumed that the syrup is an incompressible Newtonian fluid for constant density and viscosity. Lastly, we assumed that the calculations for Reynolds number is analogous between standard and Taylor Couette flows. After trial completion, we extracted the angular velocity of the inner cylinder and converted it into a linear velocity using the cylinder's radius. This velocity was then multiplied by a ratio of the radius of the circular die flow over the overall distance in container radii to obtain the linear velocity of each die droplet. Once we had this, we inserted this value into the Reynolds equation to determine the Reynolds number of each flow.
Trial 4 was the only trial that experienced turbulent flow as the 2 inner drops did not return to their original starting position or shape. Experimentally, it was determined that the cutoff Taylor number lied between 3.0 and 3.9. Theoretically, it was determined that the cutoff Taylor number lied between 0.9 and 9.1. The laminar to turbulent transition occurred in these ranges and was assumed to be the midpoint of the ranges. This means experimentally the cutoff Taylor number would be 3.5, and theoretically it would be 5.0. Drops placed closer to the inner cylinder that were moving faster had higher Taylor numbers than those that were closer to the outer cylinder. The differences between the experimental and the theoretical values were mainly due to differences in fluid velocity calculations with each. As with any experiment, there were a few sources of error that could have negatively affected the results. The camera angle made it hard to estimate how much of a revolution each die drop did, and in turn its velocity. Next was the determination of the viscosity of the Karo syrup, which relied on general values found online but was not found experimentally for our specific syrup. Additionally, the vertical position of the die drops mattered. Drops closer to the top of the fluid surface moved faster and therefore more turbulently than those placed near the container's bottom. Lastly, the Reynolds numbers were all extremely low, hinting at issues with turbulent classification or with the calculation assumptions.
In conclusion, our experiment demonstrated that Couette flow can be applied to rotational flow in addition to axial flow. We found that the rotational velocity and die mixing decreased as the radial distance from the center increased. Additional equations and more precise data acquisition, such as better regulated rotational speed and a larger sized container with more uniform geometry, would be needed to mathematically demonstrate the Reynolds transition.
We will now take any questions you have about our experiment.